Hi, my name is Jens and I believe that everybody can learn electronics. Today I want to show you how you can build your own binary clock. So that's right, this thing is a clock. And some of you might say, Jens, this is just an empty soup can with some LEDs sticking out of it. And you're absolutely right, it totally is. But it also happens to be a clock because these LEDs display the time in binary. How does it do that? Let's take a look. The first row corresponds to the hours, the second one to the minutes, and the third one to the seconds. The orange LED is the PM indicator LED in AM/PM mode, or it belongs to the hours in 24-hour mode. The left push button increases the hours, and the right push button sets the minutes. The toggle switch in the middle switches the LEDs off or on. If you hold the push buttons, the minutes and seconds will increase faster. Okay, but how do we read the time? Binary just consists of ones and zeros. An LED that is on is a 1, and an LED that is off is a 0, like that. What do the columns mean? They increase from right to left, like 1, 2, 4, 8, 16, and 32. Each time the factor gets 2 times bigger. Okay, let's look at the hours. From left to right in binary, they are 1, 0, 1, 0. This means they're equal to 0 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8, which is 10. How about the minutes? They read 1, 0, 1, 1, 0, 1, which means 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8 plus 0 times 16 plus 1 times 32, which adds up to 45. And the seconds? Well, they're a little fast to do it in real time when you're just learning binary, but I decided to include seconds in this clock because I think it looks cool and it gives you a great visual idea of how binary numbers work. In the rest of this video, I want to show you how you can build this thing yourself. So we will go through the schematic, the software that is needed to program the controller that is in here, and the third step, actually building the thing. Now, you don't have to build it exactly like this. I kind of like this look of this, this tin can, and actually use some, stainless steel drinking straws here to have like a nice thing to stand it on. You don't have to use it exactly this way. You can put these LEDs and the switches in any enclosure that you want. In this video, we're going to focus on how to build this in this housing though. All right, so let's get started and build this thing, and let's first look at what we actually need. Here are all the components you need for the binary clock. The PIC 16F883, as well as the PIC Kit 3 to actually flash the hex file onto the controller, a breadboard, 7 breadboard wires, 17 LEDs, and 17 matching resistors, 220 ohms in this case will do just fine, a USB power supply, a toggle switch, 2 regular push buttons, a 4.194304 MHz crystal, and 2 22 picofarad capacitors. It'll also be helpful to have a little bit of wire handy. And regarding these LEDs, well, you can get 12 volt ones or 5 volt ones that are already wired up with the resistor. In my case, I'll just do that myself because I don't want to pay extra. And if you want to do that, then you will also need a soldering iron. Heat shrink tubing is also really nice if you want to make your wiring look more acceptable. And this is how it looks like. It takes a fair amount of time to solder all these connections and put the heat shrink on. If you don't want to solder, don't worry. eBay is a good source for pre-wired LEDs as well as toggle switches and push buttons that come with all their wires readily attached. Shipping times can be a few weeks for these components, so keep that in mind. We also need a can. I chose a simple soup can and removed the label with some warm water. But that didn't get rid of all the glue that held the label in place. I sprayed it with an adhesive remover such as Goo Gone and let it sit for 10 minutes. After rinsing with more water, all the glue came off nicely. I did all of that with the can still unopened because it handles much more easily this way. And now, time for some chicken soup. Next to the aluminum can, we also need the feet that this can is going to stand on, and for those I just chose very simple stainless steel drinking straws. We also need pliers and side cutters, an electric drill, And in this project, we will need a 5mm breadpoint bit for the LEDs. We will need a 6mm breadpoint bit for the toggle switch, and we will need a 7mm breadpoint bit for the 2 push buttons. And no project is really complete without hot glue. But where can you buy these components? On my website friendlywire.com, you can find a companion article to this video, and it includes a detailed list of resources. Take for example the LEDs. There are 2 links. The first one brings you to an electronics distributor where you can buy a single LED or thousands of them. The second link brings you to Amazon where you can buy an LED kit. If you want to stay in electronics and build more circuits like this one in the future, buying kits instead of single components might be a good idea. Let's talk a little bit about the schematic of the binary clock. The main protagonist is the PIC16F883 microcontroller. I chose it because it has many I/O ports that allow us to connect these 17 LEDs here, as well as 2 push buttons and 1 toggle switch. It is connected to +5V over here and to ground here. The master clear pin is permanently connected to +5V to prevent the controller from resetting. The 4.194304 MHz crystal, together with these 2 22 picofarad capacitors here, is used to create a time base for the clock that ticks exactly once per second. More on that later when we talk about the programming of the controller. I arranged the LEDs in the schematic here exactly the same way that they were mounted in the final clock. The lower line here are the seconds, above it you have the minutes, and over that the hours. This LED here on the left is either the PM indicator or another bit for the hours. Each LED has a 220 ohms resistor, and its cathode or negative terminal is connected permanently to ground. Its anode or positive terminal is connected to an output of the controller. I chose labels for that purpose so that the schematic doesn't become too cluttered. The 2 push buttons that adjust the hours and minutes are connected to ports RB1 and RB2. And the toggle switch that switches the LEDs on and off is connected to pin RB0. Lastly, I also included an option to switch between the 24-hour mode and the AM/PM mode. If you want the 24-hour mode, connect pin RB3 to ground. If you want the AM/PM mode, then just leave it disconnected. And that's it. Now that we know what we need and we understand the schematic of the binary clock, we actually have to think a little bit about the microcontroller that's in here and that makes the binary clock tick. How does it work? How do we program a clock? The source code for our binary clock contains quite a lot of different aspects. Here I will give a brief description of what everything does, but if you are interested in all the details, I invite you to check out the companion article to this video where I explain the code in great detail. Right here at the beginning, we tell the controller to expect an external crystal connected to pins RA6 and RA7. This is the 4.194304 MHz crystal we just saw in the schematic. The rest of these lines is just standard initialization stuff that is not terribly important. After that, we define where we will connect each LED and button and switch. This step is optional, but I prefer to use expressions like on/off later in the code as opposed to just RB0, because then I know what it stands for and I don't have to remember it by heart. Also, it is a lot easier to change stuff around later this way. Next, we define our variables. These here will store the time information, and these other variables are auxiliary. They help us to get the 1 Hz time base and to debounce the push buttons. I wrote a whole article on debouncing buttons, and you can check it out here if you want. Then the main function begins. But we are still not done with the preparations. First, we enable the so-called pull-up resistors on port B. This is helpful because we can save some external components this way. If you want, you can read more about pull-up resistors in my article on push buttons here. The PIC16F883 is a large controller with a lot of functionality. Some of it is turned on by default, but we don't need all of it. In these lines here, we deactivate the so-called analog to digital converter, or ADC, so that we can use our pins as regular outputs. Speaking of which, in these lines here, we set the so-called tri-state registers to tell the controller which pins are inputs, where we connect the switches, and which ones are outputs, where we connect the LEDs. A 1 means input, and a 0 means output. It's easy to remember because a 1 looks like an I for input, and a 0 looks like the O from output. We're almost done with the preparation, but this part is very important. We are configuring the timer and the interrupts. If you want, you can read more about this in my article here. But the main idea is very simple. These lines make sure that one special function, which we will see below, gets called precisely 4096 times per second. We will use this to extract exactly 1 tick per second to make our clock tick. And congrats, we have made it to the main loop. This loop gets executed over and over and over again and never stops as long as the clock is turned on. If the toggle switch is turned to the on position, these lines here take the content of the variables seconds, minutes, and hours and calculate which LEDs have to be turned on or off. The hours are treated separately depending on whether the 24-hour mode is activated or not. In these lines here, we react to the push buttons. If they are pressed, either the minutes or hours are increased to set the time. This part is only executed if the LED toggle switch is set to the on position, so that we don't accidentally change the time when pressing the push buttons while the LEDs are turned off. If the toggle switch is set to the off position, then all LEDs are turned off. And that's all there is to know about the main loop. But wait, where do we do the counting of the time? Isn't that the whole purpose of a clock? Well, that is where that special function that gets called 4096 times a second comes in. It is called an interrupt service routine, or ISR for short. In this function, we increment the variable time buffer by 1 every time it gets called. If it reaches 4095, we reset it to 0, and then we know that exactly 1 second has passed. And then we can update the time. As I mentioned before, we also use the ISR routine to debounce the switches. And that is all the code. I know it is quite a lot to take in, but all that we need for this project is actually not the code, but the so-called hex file. We can generate it by clicking on the hammer symbol up here. And there you have it. If you don't want to code yourself, you can download this hex file on my website. And now we're finally done here. Now that we know what makes this clock tick, all that we really have to do, well, is build the thing, right? That consists of 2 parts. First, we have to actually put the hex file or the code onto the controller, and then we can actually build the binary clock itself. To put the hex file onto the PIC16F883 controller, we need to connect it to the computer, and we do this with the PIC-Kit3. So you can see my breadboard here. It's connected to the PIC-Kit3, which again is connected to my laptop all the way over there. But how do we connect the PIC-Kit to the PIC controller? Well, that's very easy because each controller has a few pins that do just that. So for the PIC16F883, the 5, in this case 6 relevant pins are VDD, which is just the positive supply, 2 VSS ground connections, the master clear pin, and then data and clock. And we can connect this right away. For power plus 5 volt, I like to use the red cable. So let's do this. And it's the 1, 2, 3, 4, 5, 6th pin from the bottom. So let's count 1, 2, 3, 4, 5, 6. So it's this one right here. Now there are 2 ground connections. Let's do those next. I like to use black for those. The first one is easy because it's right below VDD. So it's this pin here. The next one is on the other side, and it's pin number 8. So let's count again. 1, 2, 3, 4, 5, 6, 7, 8. It's this one here. Master clear is pin number 1. So that's easy. That's just this one right here. And then we need to connect data and clock. So on the PIC header, it's this one here. And then data is just the first one to the top right, pin number 28. and clock is right below, like so. And that's it. All right, now everything is wired up and we can move over to the computer screen here. And as you can see, I have already connected it, but just to show you how this works, let me just disconnect it again. And we click on connect. It takes a while for the controller. There is a prompt here. We just click OK because we know what we're doing. And then it is connecting. Now, you might get an error message at this point because under power here, you have to make sure that we're actually powering the device, the target circuit from the tool. So we have to click that. That has to be checked. And if that's the case, we can go back to operate. We can load our hex file here. And once we've loaded this, which I've already done, we can click on program and see what happens down here. It says it's programming, and programming is complete. And while we click this, these LEDs here, they were just blinking happily along. And now the hex file is successfully transferred onto the PIC. All right, now that we have flashed the hex file onto the controller, we can actually start building the binary clock breadboard itself. I like to start by putting in the power supply module like this, and then the PIC controller. Somewhere in the middle is fine. And now we need to connect all the different wires. And I'm going to do this similar as last time when we built something. I'm going to superimpose in this video the circuit diagram, and I will draw the lines that I'm actually connecting as I'm connecting them on the breadboard. That makes it a little bit easier to follow what's going on. So as usual, I start with the power supply. And this piece of paper that we used before, I'm just going to put that next here so you don't see this, so it doesn't mess up the screen, but I can see this and it helps me wire it up correctly. So I'm going to start again with the positive supply. It goes from the 6th pin from the bottom on the right side. 1, 2, 3, 4, 5, 6. That's the one. I'm going to do ground next. So right under VSS. And then on the other side, there is another ground connection, and that is the 8th pin from the top. So 1, 2, 3, 4, 5, 6, 7, 8. That's this one. And now I have to connect master clear permanently to plus 5 volts, and that's just so that the PIC doesn't keep resetting. So it's just this pin as before to plus 5 volts. Next we have to connect the crystal, and it goes between pins 9 and 10. So those two, 9 and 10 here. In order to do this, we just sort of put it in like this. And now we have to plug in the 2 capacitors. And as you can see, I cut the leads of the capacitors down a little bit. So now they're a little bit shorter from what you saw before, so that they don't stick out that far. And all we have to do is now connect the 2 pins of the crystal we just put into ground. And that's very simple. Goes like this. And the other one like this. If you want to use the 24-hour option of this clock, we have to put pin RB3 to ground. And pin RB3 is pin number 24 on the controller here. So as we just count down, this is 28, 27, 26, 25, 24. That's the one, pin number 24, and you would have to put it to ground like this. I don't want to use the 24-hour format because 3 years ago I moved to North America and I'm still struggling with learning the PM thing. So, you know, maybe this clock will help me. So I'm just going to rip that wire right out again. But if you want it, that's how you do it. All right, that's all we can do with the breadboard at this point. The rest is going to be connecting the switches, connecting the toggle switch, all the LEDs, and let's do that next. Oh, and I just realized those 2 jumpers here, they're still set to the 3.3 volt configuration. So make sure they're pointing to the 5 volt configuration like this. All right, now it's the moment of truth. We have to start drilling our aluminum can. We're going to flip this over. So the opening is going to be towards the bottom. We have to remember this. And then I can take one of the breadpoint drill bits here and kind of like make little marks and indentations where I want to drill the holes for the LEDs. So it's a little bit hard to make these indentations, but it's going to help us later on to center the drill, so I think it's probably worth the trouble. Alright, so I have put my pilot hole locations in here, and you can probably see them a little bit, except for here, where I screwed up a little bit, but I think, I'm okay. So it's a DIY project at home, right? So mistakes happen. And now I'm going to take my drill and drill these out really carefully. The important thing to remember is to go really, really slowly, and also to hold it firmly in your hand. So I've been drilling for a while, and now you can see that there is a hole in the middle, but there is also a circular incision around this hole. And this is exactly what I meant. The drill bit is cutting into this piece of the aluminum tin, and it's going to get through, and it's going to go for give us a really nice and clean cut. So we want it this way. We don't want to push too much. We want it to cut the aluminum. And there we go. And you see, it's a very nice and clean looking hole that we just drilled. Now we have to drill all these other holes. Let's do it. Oops. Well, that one was with too much pressure, so, well, I could kind of save this a little bit, but I have to go very slowly. All right, so it's not perfect. See, we kind of got away from me a little bit. I think the rest is fairly consistent, and this is hand drilled, right? I don't have a drill press here. So I think this is, for me at least, this is good enough. And now that we have drilled the holes for the LEDs, we have to drill the holes for the push buttons and the toggle switch. So I want to align them somehow. Here's this line on the back, and this is the center. And the center should be the on and off switch for the LEDs. So I'm gonna do like a pilot hole for this thing again. And then on both sides is going to be where we put the buttons. So one of them is going to be here. And then one to the side, roughly here. I'm going to drill this exactly the same as before. And it fits. And this is how it looks like. So, and now we have to put in the LEDs. But before we do that, I want to mount the stands that are made from these stainless steel drinking straws. And for that, we're going to use some hot glue. It's easy. One of them is going to be just on the back side, like so. So we have to take our glue gun here. And we can take quite a lot of hot glue, actually. That's all right. And now we just have to move a little bit quickly and put this on the inside. Try to get it somehow perpendicular. And the other ones are going to be here and here. Like that. And I can't believe how fast that sets. And now let's see. Yeah, I'm actually impressed that this turned out so well. Okay, so how do we get the LEDs in there? I mean, they all look like this, which is really nice, but we have to mount them in there somewhere. So one of the things we're going to do is we're going to tilt them by 90 degrees, like this. And then we can also add a dab of hot glue to somewhere around here, and that's going to make the LED stick when you plug it in from the inside. And it's done. It didn't turn out exactly the way that I wanted. Some LEDs are a little bit crooked, but I think it could be a lot worse. This much. That would have saved me probably an hour or two. So yes, let's do it. All right, so let me show you how this works in principle. So all the black ones are now connected here, and then the blue cable goes over here to the negative terminal of my power supply, which is set to +5 volts. And there are all these blue wires that go to the plus pole of any of these LEDs. So how can I find out which one? Well, I just take the positive terminal and connect it to one of those, say to this one. And then I see, well, one LED just turned on. In this case, it's the third LED of the seconds. I call it S3. And then if I connect it to something else, then you see, oh, now the sixth one of the minutes turns on. Or if I turn on this one here, see, oh, that's the PM indicator. So that's just how I'm going to go through all these wires, check out which LED corresponds to which wire, and then plug it in here. I'm also going to be using this sketch that I showed earlier to locate all the LED connections on the PIC controller. Yeah, so everything is connected, including the switches. And yeah, let's see if this works. So I'm going to take the USB cable here, let's plug this in. And well, I mean, I'm not sure if you can see this, but it looks like it's a success. It's alive. So now what? Because now that it's working, as great as that is, we have to find a way to compress these wires and put it in here, preferably with the USB cable sticking out the bottom so we can still plug it in and out. So that's going to take a little bit of tweaking, but hey, I mean, the clock is alive, so that's great. So now that it's still working, I'm going to use some cable straps and kind of like zip it into place so that it doesn't move around that much. And it's working. All right, we're finally done, thank goodness. I also added a dab of hot glue to both sides of the breadboard as well as to the USB power supply so that it sits in there more securely. And there you have it, we built the binary clock. So there is one thing that I didn't talk about yet, and that is the power supply. Now, of course, we plug it in via USB from the bottom and that works just fine, but what if we plug it out by accident? Well, then the clock loses all its time, and you know, if you plug it back in again, well, it starts at, what is it? It starts at 12 a.m., midnight. That is why I recommend to connect the binary clock to a battery bank and not directly to a wall outlet. If you have a battery bank, it's mainly independent from the mains outlet, and also these things can be charged individually. So you can always charge these, disconnect these, and the clock will always keep going, and the battery bank will serve as a buffer. I really enjoyed building this binary clock, and I hope so will you, because it's a really fascinating project. It's really rewarding to hold this thing in your hand and say, well, I built this thing. I built it, I understand how this works. It's amazing and it's actually useful. How about that? Let me know if you have questions, comments, suggestions. I'll do my best to answer them all. There is also a companion article to this video on my website, friendlywire.com, and I'll put the link right here. This article is basically a written version of this video with more in-depth information and cross-references to other articles on my website. It has a detailed list of all components and tools that are needed for this project, as well as step-by-step building instructions, an explanation of the source code, and much more. So thank you so much for your interest, for tuning in, and I'll see you next time.